As we learned last lecture, a vitally important part of your home's performance as an enclosure is its ability to shed rainwater and melting snow, and then to keep this precipitation from entering the building envelope through the foundation. But this function can only be performed successfully if all of this storm runoff is conveyed away from your home and returned to a natural watercourse without causing flooding along the way. How is this actually accomplished? The answer is found in a process called site design, typically performed by civil engineers. The site design process can be applied to a single building lot, but it's most often applied to an entire development consisting of multiple residential or commercial properties. The site design for a development deals with all aspects of physical layout and integration with local civil infrastructure systems, to include the design of streets, parking lots, and cul-de-sacs, local water supply, wastewater disposal, and storm drainage, as well as modification of the Earth's contours through earthwork or grading. A site design can also be significantly influenced by such considerations as environmental impact, historic preservation, zoning, and real estate. And for this reason, it's usually very tightly regulated by local codes. In this lecture, we'll focus primarily on the storm drainage design and earthwork elements of site design. Then we'll begin a 3-lecture segment on water supply, water distribution, and wastewater disposal. And later in the course, we'll look at road design in our lectures on transportation engineering. In the world of everyday engineering, we encounter water in many different forms. But regardless of whether we're talking about supplying purified drinking water to your home, dumping household wastewater into your municipal sewer system, diverting storm runoff away from your foundation, or pumping groundwater out of your basement, we'll always deal with water by applying underlying scientific concepts from 2 specialized disciplines of engineering science called hydrology and hydraulics. And in the context of storm drainage design, the easiest way to distinguish between these 2 fields is that the science of hydrology helps us define the problems, while the science of hydraulics helps us devise technological solutions to these problems. Hydrology. It's the study of the natural movement and distribution of water above, on, and below the surface of the earth. The science is best understood in the context of the hydrologic cycle, a conceptual model describing the continuous circulation of water in the atmosphere, on the Earth's surface, and underground. Although water covers about 70% of the Earth's surface, only about 0.1% of it has any chance of directly influencing everyday engineering. This relatively small quantity of water originates as precipitation, which condenses from water vapor in the atmosphere and falls to the ground in the form of rain, sleet, or snow. Some of this water percolates down into the soil and is eventually collected in porous underground strata called aquifers. And as we've seen, this stuff is called groundwater. The remaining water from precipitation flows over the Earth's surface, initially in a very thin layer called sheet flow, which moves downhill across the surface of the ground, and then eventually concentrates in ditches, streams, rivers, lakes, and oceans. Along the way, some of this surface water evaporates, thus returning to the atmosphere, where the hydrologic cycle begins anew. Storm drainage design is primarily concerned with surface water, and while this stuff constitutes a tiny portion of the Earth's water supply, it can cause big problems for homeowners and developers. As we've already seen, if precipitation that falls on your lot isn't directed away from your house, some of it will seep into the soil around your foundation and may find its way into your basement. And if your lot adjoins higher ground, storm runoff will generally flow from that ground onto yours, exacerbating the challenge of conveying surface water away from your foundation. Furthermore, anytime land is developed, large areas of porous ground are covered over with impervious pavements and rooftops. In this photo, look at how much of the land area that was once open ground is now covered with impervious materials. As a result, significantly less precipitation infiltrates down into the soil, and significantly more flows over driveways and streets. This increased surface flow can cause flooding, inundation of municipal storm sewers, and the depletion of groundwater, which might be used for local water supply. Storm runoff can also become polluted, accumulating metals from gutters and downspouts, hydrocarbon residue from pavements, and fertilizers and pesticides from lawns. Storm drainage design must address all of these challenges, primarily through hydraulics, a scientific field that's broadly concerned with the mechanical properties and engineering applications of fluids. The hydraulics concepts most relevant to everyday engineering are mathematical models used to characterize the flow of water through closed pipes, like these water supply lines, and through open channels, like ditches and river valleys, both natural and man-made. To illustrate how hydrology and hydraulics have influenced the piece of terrain on which your home is situated, let's walk through the process a civil engineer would use to design a storm drainage system for a typical suburban land development project. Here's a large tract of open land in a suburb of the city where I live. It's bounded by a stream on the east side, a golf course on the south, and older residential developments on the north and west. A developer has purchased this 54-acre plot of land and has received the necessary permits to build a large residential development of single-family homes on it. In this exercise, we'll play the role of the developer's civil engineer, charged with preparing a comprehensive stormwater management plan and getting it approved by the municipality. But before we can begin our design, we must first familiarize ourselves with one of the site designer's principal tools, the topographic map. Here's a topographic map of our project site. And by the way, you can obtain these maps for any place in the United States from the U.S. Geologic Survey. Paper maps cost only a few bucks, and the digital versions can be downloaded for free from the USGS website. The brown lines on our topographic map are called contour lines. They're imaginary lines of constant elevation that allow us to visualize a piece of terrain as a three-dimensional entity. On this map, the specified vertical distance between the contour lines, which is called the contour interval, is 10 feet. Therefore, if I'm walking along this path, I'm walking on level ground at a constant elevation of 350 feet above sea level. Now, if I turn and walk about 400 feet eastward, I've crossed two contour lines. So I've actually descended 20 feet to an elevation of 330 feet above sea level. Now, to illustrate how we can use contour lines to visualize three-dimensional terrain, I'll start with a two-dimensional computer model of our USGS topographic map and then extrude it upward into the third dimension in intervals of 10 feet for each contour line. Now we can clearly see that closely spaced contour lines correspond to a steep slope and widely spaced contours to a shallow slope. A single contour forming a closed loop, like this one, is usually a hilltop, as you can see here, but could also be a depression. In river valleys, the contour lines form a distinctive V shape, like this one, and the V always points upstream. Thus, we know that the water must be flowing in this direction. Now, armed with our topographic map, we can now execute the first step in the storm drainage design process, delineating the watershed of our proposed development project. A watershed is an area of land defined such that a drop of rainwater falling anywhere within its boundaries eventually drains to the same outlet. Let's see what this really means. Here's a three-dimensional model of the terrain on which our residential development will be sited, oriented with north facing toward me. In building this model, I've used alternating layers of different colored wood so you can see the contours more clearly. I'm now going to use this squirt bottle to deposit a stream of precipitation at various locations on the model so we can follow the path of the resulting surface flow. Notice as I deposit streams of precipitation that water will always flow perpendicular to the contour lines. Watch. There's a pool which turns perpendicular to the contour in every case. The reason that phenomenon occurs is that the perpendicular path across contours is always the shortest distance between those two contour lines. And therefore, the shortest distance for a given vertical change in elevation must be the steepest slope. Now, as I did these examples, you probably saw that rain falling anywhere along the south side of this ridgeline will always flow southward into this stream bed. And again, you see that phenomenon here. No matter where I deposit the water, it always ends up going generally to the south and landing in the stream bed. However, if I deposit rain just a short distance to the north on the opposite side of the ridge, all of the water will flow in the opposite direction. And no matter where I deposit it, that water will eventually be collecting at the low area here, picked up by this draw and channeled down ultimately into the river valley, which extends beyond my map up here to the north. So once again, I'll deposit water here. It eventually follows that roadway down, crosses over at the low spot, and ultimately departs from our project site. And once again here, as long as I'm on the north side of the ridgeline, the water is ultimately going to end up in that same draw. Since all the rain falling within the boundaries of our project site ultimately collects at this low point on the northern boundary, we're going to designate it as the outlet of our project watershed. Now, a watershed can be very large or very small, and the large ones can be subdivided into an infinite number of smaller ones. For example, the vast Mississippi River watershed covers about 40% of the lower 48 states. The Ohio River watershed is contained entirely within the Mississippi watershed, and myriad smaller watersheds of tributary streams are contained within the Ohio. A watershed can also be defined for a specific project site, though at this small scale, it's often called a catchment rather than a watershed. Regardless of size or terminology, the delineation of a watershed always derives from the point designated as the outlet. Which brings us back to our residential development site, for which we've designated the outlet here at the low point along the northern boundary. Now, recognizing that surface water always flows perpendicular to contour lines, except where it's intercepted by streets, I can represent the direction of flow with a series of blue arrows placed at representative locations all over the map. And now it should be quite clear that the watershed boundary follows this path along the ridgeline to the south and streets to the west and north, and then back to the outlet. Note that rainfall landing anywhere within this region will eventually reach the outlet, and rain falling anywhere outside this region will end up elsewhere. Next, we'll define something called the design storm, which will serve as the basis for designing the entire drainage system. The design storm is typically defined in the form of a graph called an intensity, duration, frequency curve, or IDF curve. Each region of the U.S. has its own characteristic set of IDF curves, which are developed by the National Oceanic and Atmospheric Administration, or NOAA, from long-term statistical data on storms experienced within that region. Here are the IDF curves for the location of our project site. You can download these data for your own region from the NOAA website. Note that each plot shows the relationship between storm intensity, measured in inches of rainfall per hour, and storm duration in minutes for a representative storm with a particular recurrence interval, 100 years, 50 years, 25 years, and so on. Now, the recurrence interval is the statistical average period of time between occurrences of a storm with this particular severity. Thus, for example, a storm with a 100-year recurrence interval, the proverbial 100-year storm you've heard about on your local TV weather report, will happen on average once every 100 years. The recurrence interval is actually just a measure of probability. The mathematical probability that a given storm will happen in a given year is 1 divided by the recurrence interval. Thus, the probability of experiencing a 100-year storm in any given year is 1 divided by 100 equals 0.01 or 1%. The probability of a 25-year storm in any given year is 1 divided by 25 equals 4%. In general terms, a storm with a longer recurrence interval is both more severe and less probable than a storm with a shorter recurrence interval. A word of warning here. Just because it's called the 100-year storm doesn't mean a storm of this severity is guaranteed to happen exactly once in 100 years. A storm is a random event, like flipping a coin. On average, we should get one head for every 2 flips of this coin. But we know that for any given pair of flips, we might also get no heads or 2 heads. In the same way, a given 100-year period might have no 100-year storms, or it might have several. Note also that for each curve, a storm of short duration has a higher intensity than a storm of longer duration. This just makes sense. An intense downpour generally doesn't last very long, and long-lasting rainstorms usually aren't very intense. Local building codes usually specify which recurrence interval is to be used for storm drainage design in the associated jurisdiction. For our project, the code specifies 50 years, so we'll be using this IDF curve for our design. Now, we're ready to perform a hydrologic analysis of the catchment area using a standard analytical technique called the rational method. At the heart of the rational method is this mathematical equation, Q equals CIA, which is used to calculate the maximum rate of storm runoff that will flow through the outlet of our drainage system during the design storm. This maximum runoff, Q, is measured in cubic feet per second. It's also called the discharge of the watershed. A is the area of the watershed in acres. And for our residential development project, that's 70 acres. Note that the watershed extends beyond the boundaries of the 54-acre project site. Thus, stormwater will flow onto the site from these regions and must be considered in the design. C is called the runoff coefficient, an empirically derived parameter that's based on the permeability of the ground surface within the watershed. For our project site, prior to development, the relatively flat pasture land has a runoff coefficient of 0.37, meaning that only 37% of rainfall will flow over the surface, while the remaining 63% will seep into the soil and become groundwater. In contrast, a concrete surface has a runoff coefficient of 0.9, the higher value reflecting the fact that most rain falling on concrete will run off rather than soaking in. Finally, I is the intensity of the design storm in inches of rainfall per hour. But referring back to our IDF curve, how do we determine an appropriate intensity when the curve ranges from a maximum value of 7 inches per hour all the way down to a minimum of less than 2? Well, to answer that question, the rational method assumes that the maximum possible discharge occurs when the entire watershed is contributing to the flow. To represent this condition mathematically, we'll calculate a parameter called the time of concentration, defined as the time it takes for a drop of water to flow from the most remote point in the watershed all the way down to the outlet. Once that drop of rainwater has flowed from this point overland along this path to the outlet, then we'll know that the entire watershed must be contributing to the flow because every other possible path to the outlet is shorter. Now, over the years, engineers have developed a variety of different empirical equations to estimate the time of concentration. Believe it or not, this is one of the simpler ones. Regardless of which equation is used, the time of concentration will always depend on 3 factors: the length of the flow path, the slope of that path, and the roughness of the ground surface. When I substitute the appropriate values for our project site, the resulting time of concentration is about 24 minutes. Now, returning to our IDF curve, we'll use this period of time as the duration of the design storm, and the resulting intensity, 4.2 inches of rainfall per hour, represents the most intense storm that will have the entire watershed contributing to the flow. Finally, we can substitute our values for the runoff coefficient, intensity, and watershed area back into the rational method equation, and the result is a maximum discharge of 109 cubic feet per second. To put this result into somewhat more understandable terms, that's over 800 gallons of water flowing out of the watershed every second. And from this point, the only place for it to go is across the street. So it's quite likely that this road experiences significant localized flooding in heavy rainstorms. Now let's repeat the calculation for the same piece of land, but with the developer's planned layout of streets, cul-de-sacs, houses, and driveways superimposed over the map. Because of all these impervious surfaces, the runoff coefficient C increases from 0.37 up to 0.46. That means that significantly more rainwater runs across the surface rather than soaking into the ground. Meanwhile, the time of concentration drops to 17 minutes because the runoff will now flow across paved surfaces for about half of its journey. Returning to the IDF curve, the shorter time of concentration requires that we design for a storm of significantly higher intensity, 4.4 inches per hour. Updating our calculation, Q equals CIA, the overall effect is that the post-development storm discharge is now 142 cubic feet per second, a 30% increase over the pre-development discharge. If all this extra water isn't properly managed, it's going to cause two major problems. First, during heavy storms, torrents of water flowing over the road surfaces within the development are going to cause a safety hazard for drivers. The design engineer will address this challenge by incorporating a storm sewer system into the site design. Now, a storm sewer is a network of underground pipes that collect stormwater and convey it to a nearby watercourse, lake, or ocean. The storm runoff enters the system through these inlet structures. Above ground, the inlet is typically a steel grating or curb opening like this one. Below ground is a precast concrete box with large holes to accommodate the incoming and outgoing pipes. The pipes themselves are often concrete, though iron, steel, and plastic are sometimes used as well. They run from inlet structure to inlet structure, arranged in a tree-like network with small branches feeding into larger trunks, and these feeding into even larger main lines. All pipes in the system are placed on a steady downhill slope, so water will flow through the system by the force of gravity alone. The resulting network looks a lot like a natural river system, with a large river fed by many streams, each of which is fed by even smaller tributaries. And this similarity is hardly surprising, since the storm sewer serves essentially the same function of collecting and draining precipitation from a large area of land. Now, in designing this system, we would first determine appropriate locations for the inlet structures. These are placed at a minimum at low points in the road network to prevent water from pooling here, and immediately uphill of intersections so that storm runoff doesn't create a safety hazard by flowing across the intersection. Additional inlets are often added at regular intervals to intercept the flow so the inlet structures at the low points don't get inundated in large storms. With the inlets positioned, the science of hydraulics provides us with all of the analytical tools necessary to determine the size of each pipe such that it can carry the accumulated discharge from the inlets and higher level pipes, and the slope of each pipe such that the velocity of flow is high enough to prevent sediment from accumulating in the pipe. It's both surprising and impressive to see how much engineering goes into a system that's almost completely hidden from view. So now our project site has a shiny new storm sewer system to keep water off the streets within the residential development. But we still need to contend with a second major challenge, the substantial increase in discharge at the outlet. If we don't do something about the 1,000+ gallons that will accumulate here every second during the design storm, it's surely going to flood the main east-west road. Now, a partial solution would be to route this discharge into a catch basin like this one and carry it directly to this stream through a large underground pipe. At the termination of this pipeline, we'll add an outfall structure like this one. It's designed such that any sediment being carried along by the stormwater will be deposited into this bed of coarse stone rather than being dumped into the stream. But this pipeline is really only a partial solution because, as you'll recall, our development has increased the total discharge from this watershed by 30%. Dumping all this additional water into the stream will only increase the likelihood of flooding downstream. And with each new housing development, shopping mall, and business park, the likelihood of flooding is only going to increase. For this reason, today, many municipal codes specify that the maximum post-development storm discharge can't exceed the pre-development discharge. But how is this even possible, given that development always causes runoff to increase? Well, the answer is to incorporate a stormwater detention pond into the site design. A detention pond is an earthen enclosure, typically located near the outlet of the development's storm drainage system. Storm drains discharge into the basin at outlet structures like this one. The basin stores the runoff temporarily, allowing some of the water to infiltrate into the soil and some to evaporate. Peak runoff from large storms is released at a controlled rate from an outlet structure like this one into a local watercourse or an existing storm sewer line. In recent years, there's been growing awareness of the pollution that storm runoff accumulates from roofs and yards and parking lots. In response, many local standards for detention ponds also require water treatment, typically achieved by allowing sediments to settle out of the impounded water, by allowing more of the impounded water to infiltrate into the bed of the pond, by filtering runoff water before it's discharged into the storm sewer system, and even by providing some level of biological water treatment through the deliberate creation of a wetland marsh on the floor of the pond. We'll see how this natural water purification process works in our upcoming lecture on water treatment. Our site design now includes a storm sewer system to keep stormwater from accumulating in the streets, and a detention pond to ensure that the maximum post-development discharge doesn't exceed the pre-development discharge. But one piece of the puzzle is still missing. Our design must also provide pathways for precipitation that falls on rooftops and unpaved areas to flow overland to the storm sewer inlets without flooding basements, creating unwanted ponds, eroding hillsides, or flooding streets. To a large extent, this need is fulfilled through earthwork, also called grading. In general terms, grading reforms the topographic contours of the project site for compatibility with the intended land use. This model shows the natural flow of storm runoff across a portion of the undeveloped project site. Now let's add a house. And note that this building interrupts the natural pattern of flow, causing water to accumulate at these two uphill walls, and almost inevitably leading to water infiltration problems. We'll meet this challenge by grading the site to modify the pattern of overland flow. We'll ensure that the soil around the foundation and the driveway are sloped away from the house. And we'll sculpt the uphill portion of the yard into a swale, which will divert the flow around the building and down to the street, where the overland flow will be captured by a storm sewer inlet. And so the grading plan works in tandem with the storm sewer, street, and detention pond designs, fundamentally altering the movement of precipitation across and underneath the project site, all for the purpose of moving water away from our homes. Ironically, we still need quite a lot of water inside our homes, and it takes a separate and even more complex infrastructure system to meet this most basic of human needs. Next lecture, water supply.